Before the mid-20th century, diseases like typhus and malaria caused global devastation. In the absence of modern insecticides, these pathogens spread unchecked through entire populations, often overwhelming medical infrastructure. The logistical pressure of World War II intensified the search for a solution. With millions of troops deploying into tropical environments, militaries viewed insect-borne illness as a threat to their operations that was just as dangerous as any enemy army. In 1939, Swiss chemist Paul Hermann Müller identified a potential solution: dichloro-dichlorophenyl trichloroethane, or DDT. Müller was awarded the 1948 Nobel Prize for demonstrating how this laboratory compound could function as a highly efficient contact poison. Its low cost and high efficacy seemingly offered a permanent escape from age-old diseases. The chemical works by attacking the insect's nervous system. A mosquito in midair can be effectively frozen by a microscopic dose.
The DDT molecule binds to voltage-sensitive sodium ion channels in the insect's neurons, jamming these gateways permanently open. Sodium ions flood the cell without interruption, causing spontaneous firing. This systemic overload leads to uncontrollable, fatal spasms. Unlike previous insecticides, DDT remains active on a surface for months. A single application can kill every mosquito that rests on a treated wall long after the initial spray. This persistence allowed public health officials to break the transmission cycle. When integrated with improved sanitation and better housing, these spraying campaigns helped eliminate malaria across North America and Europe by 1951. Following the war, usage shifted from targeted disease control to industrial-scale agriculture. By 1959, the United States alone was applying 36,000 tons of DDT to crop fields annually. Two chemical traits define the molecule's behavior. It is hydrophobic, meaning it repels water, and lipophilic, meaning it binds easily to fats. Because it cannot be washed away by rain, it is absorbed directly into the fat stores of living organisms. This leads to biomagnification. As the chemical moves up the food web, it doesn't dilute. Instead, it reaches highest concentrations in apex predators. In birds of prey, the toxin inhibits calcium ATPase, the enzyme needed to form hard eggshells. As a result, the eggs of bald eagles and peregrine falcons became too fragile to support the weight of the mother. Across North America, populations crashed as reproduction rates failed to keep pace with the toxic buildup. By the 1960s, a growing body of evidence linked DDT to catastrophic declines in wildlife and a persistent presence in the human food supply. Rachel Carson's 1962 book, Silent Spring, synthesized these concerns, arguing that the indiscriminate use of persistent pesticides threatened both the environment and human health. Further research classified DDT as an endocrine disruptor and a probable human carcinogen. Studies began showing that long-term exposure could interfere with human reproductive health and thyroid function. These findings forced a global policy shift. The United States issued a domestic ban in 1972, followed by dozens of other nations, culminating in the 2004 Stockholm Convention, which restricted the chemical globally. For decades, it appeared that the era of persistent organochlorines had come to a definitive end. Despite the global ban, DDT is still manufactured and used today. This is because malaria remains a primary public health challenge, causing an estimated 438,000 deaths in 2015 alone. This chart shows the discrepancy in scale between usage types. The environmental damage of the 20th century was driven by massive agricultural application. For comparison, spraying 40 hectares of cotton required as much DDT as treating 1,700 homes. This excessive agricultural use also drove rapid evolutionary resistance. By flooding ecosystems with the toxin, humanity forced mosquitoes to adapt, rendering the chemical ineffective in many regions where it was needed most. This suggests that it was the unchecked scale of commercial usage rather than targeted disease control that created the toxicity crisis and compromised our ability to fight the parasite. Today, the World Health Organization only endorses DDT for a practice called indoor residual spraying. By applying the chemical only to the interior walls of homes, health workers can repel or kill mosquitoes while keeping the toxin isolated from the broader environment. This method leverages the chemical's irritation factor. Even biologically resistant mosquitoes will violently fly away from a treated wall before they can bite. This leaves epidemiologists with a difficult choice.
They must balance the documented risks of endocrine disruption against the immediate acute mortality of malaria. The history of DDT illustrates that in public health, there are often no perfect solutions, only a rigorous, ongoing calculation of the lesser of two evils.